Hey Global Impact students, this is Mr. Ellinger. This lesson is on permutations and combinations. In this lesson, our learning target is to count permutations and combinations. Essential understanding: multiplication can be used to count the number of ways that certain things can happen. One of the ways that we can count the number of ways that things can happen is called the fundamental counting principle. And it says that if event M can occur in M ways, little m, and is followed by event capital N that can occur in n ways, then event M followed by event N can occur in little m times little n ways. Basic example: if you have 3 pants and 2 shirts, take 3 times 2, that equals 6. That tells you how many possible outfits there are that you can make out of 3 pants, 3 pairs of pants and 2 shirts. And here in the blue box, it gives us an example of why it works. We can make what's called a tree diagram. So we can see that there are 3 groups of 2 outfits, and they're all based off of or branched off of a pair of pants. So your first pair of pants, you can have one of 2 shirts that you wear with it. Your second pair of pants, you can have one of 2 shirts to wear with it. And your third pair of pants, you can have one shirt or another shirt to wear with it. That's where you get your 6. So that's called a tree diagram. In 1966, one type of Maryland license plate had 2 letters followed by 4 digits. How many of this type of license plate were possible? Well, if you think about our license plate, here's our rectangular license plate. And in this license plate, we're going to have 2 letters followed by 4 numbers. So the question is how many possibilities go in each spot? Well, in these first 2 spots, we have 26 letters, right? 26 letters in the alphabet. So there's 26 possible characters, if you will, that could go in this box, 26 possible characters that could go in this box. In these last 4 boxes, we have digits, single digits. Can be 0 up to 9, so that is 10. So there are 10 possibilities in each one of these spots. All right. And then what we have to do here is we have to multiply all this together. So the way that we would answer this or calculate this is we would do 26 times 10 times 10 times 10 times 10. And that would give us a value of 6,760,000. That's how many license plates there are. Okay, so one way that we can count how many ways something can take place is what's called a permutation. And so a permutation is what we call an arrangement of items in a particular order. And in that sentence, you will see 2 key words: arrangement and order. Those are key words for a permutation. Suppose you wanted to find the number of ways to order 3 items. There are 3 ways to choose the first item, 2 ways to choose the second item, and 1 way to choose the third. By the fundamental counting principle, there are 3 times 2 times 1 permutations. So using factorial notation, you can write 3 times 2 times 1 as 3 exclamation point, and that's red, 3 factorial. So for any positive integer, n factorial is defined to be n exclamation point, and the way we expand that out or write that out is to take n, multiply it by a quantity n minus 1, so decrease n by 1, and continue in that pattern, decreasing by 1 by 1 by 1, all the way until you get to 3 times 2 times 1 at the end. Okay, so let me give you a different example here. We had 3 factorial. Let's look at 8 factorial. Not too bad to write out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is 8 factorial. Okay? So that's how we write out a factorial. Is to just start with the number here and just multiply it by numbers decreasing by 1 every time until we get down to 1. Okay? An interesting little item here. We are going to go ahead and define 0 factorial to be 1. All right. If you think about 0 factorial in the sense of the definition here, 0 factorial says to multiply everything from here down to 1. Well, if you start with 0 you can't really multiply it by anything decreasing by 1 to get to 1, because it's already past 1, if you will, less than 1. So this is just a definition, what we call an axiom, that has to be assumed to be true in order to carry out many of the problems that we're going to look at. Okay, so a problem here: in how many ways can you arrange 8 shirts on hangers in a closet? So we're taking 8 shirts and we're going to put them in order in a closet. And you see the word arrange. So we know this is what's called a permutation. And this is a basic permutation. So we just have to figure out 8 factorial. And I just wrote above what 8 factorial looks like. If I go ahead and calculate 8 factorial, I get 40,320. So think about that. I'm sure you probably have 8 shirts in your closet right now. You could arrange those 8 shirts 40,320 different ways. And that seems like a absurdly large number for this situation, but if you go to your closet and take 8 shirts and start putting them in order and keeping track of the order that you're doing it, I think fairly soon you're going to realize, man, there really are a lot of these, because however you wanted to label your shirts, if you put one particular shirt in the first place, you have 7 options for the second place, and then 6 for the third place, and so on. But then as soon as you change the shirt in the second place, then you have a bunch of different options from there, and so on. So these, sometimes these numbers, this 40,320, doesn't seem logical at first, but when we start to think about, okay, wow, there really are a lot of possibilities here, it seems to, ease our mind fairly quickly. Okay, so many of the permutation problems that we're going to do are not going to involve just taking 8 things and arranging all 8 of them like the last example. A lot of times what we're going to do is we're going to have a set of items, say 10 items, and we're only going to arrange 5 of them. So we're going to have a way that we can calculate that or do that. Okay, so that's what's in this text box here. We have a key concept, number of permutations. So the number of permutations of n items of a set arranged r items at a time is, and this right here is some notation, okay, it's a little n, a capital P, and a little r. Okay, the n and the r are called subscripts. Okay, they almost look like exponents, but they're down kind of bottom right and bottom left of this capital P, not upper right, where an exponent would typically be. So these are called subscripts. Exponents are called superscripts. So here we have n, p, r. So this means we're going to have n items, and we're going to choose r of them to arrange them. And this is how we calculate this. So this is our formula for permutation. We have n factorial over the quantity n minus r factorial. We have this condition here that says r has to be between 0 and n. R could equal 0. R could equal n, but r cannot be greater than n. And if you think about that, it should make sense, because if we have n total items, we can't choose more than that to arrange them. So r has to be less than or equal to n. So here's an example. If we had 10 items and we're going to choose 4 of them to arrange, this would be what we call a 10 choose 4 permutation. So we would have 10 factorial over the quantity 10 minus 4 factorial. Well, 10 minus 4 is 6. So we'd have 10 factorial over 6 factorial, and that value is 5,040. So here's an example. Part A here, it says, in how many ways can 15 runners finish first, second, and third? Okay, now I know we're talking about permutations right now, so it's obvious that we're going to do a permutation here, but the way that we know this is a permutation, because we're going to have different types of problems here in just a second, the way that we know that this is a permutation is to look at this and say, okay, I'm taking 15 runners and we're choosing 3 out of that, but not only are we picking 3, but we are assigning them a place: first, second, third. That is arranging or ordering, okay, or classifying. Okay, anytime you put things in a particular order or arrangement, it's a permutation. So this is a 15 choose 3 permutation. Okay, and the way that we calculate this is 15 factorial over 15 minus 3, which is 12 factorial. Okay, and our calculators, we can do a lot of this on our calculator. We have to be careful. Nice thing about our TI calculators is there are permutation and combination buttons on there where we just have to tell it what N is and what R is, and they will calculate this for us. I just want to show you here briefly how you could do this without a permutation or combination button or without a fancy calculator. Really, you could even do this by hand. Okay, it might seem crazy, like how can I multiply 15 times 14 times 13 times 12 all the way down to 1 and then divide that by 12 times 11 times 10 times 9 times 8. Okay, doing it that way would be rather daunting, but let me show you how this works. 15 factorial in my numerator means 15 times 14 times 13 times 12 all the way down to 1, but I'm going to stop here. 15 times 14 times 13 times 12 factorial is a way to expand out 15 factorial, or write out 15 factorial. And the reason I'm stopping at 12 factorial is because I have 12 factorial in my denominator. Okay? So if I just ignore the 15 times 14 times 13 for a second, and I just focus in on the 12 factorial in the numerator and the 12 factorial in the denominator, 12 factorial in the numerator, 12 factorial in the denominator, that gives me a value of 1. I don't really know what 12 factorial is. It doesn't matter because I have the same value in the numerator and the denominator. So those two, essentially what we say, cancel each other out. Okay? So what that leaves is 15 times 14 times 13. And we can do that by hand. And when I multiply that, that gives me 2,730. So the answer for part A, 15 runners, how many different ways can 15 runners finish first, second, or third? There are 2,730 ways. Okay. Part B, in problem 3, the number of ways, or in this problem here, is the number of ways for runners to finish first, second, and third the same as the number of ways to finish 8th, 9th, and 10th? Okay, well, what do you think about that? If you think about it for a second, whether they finish first, second, or third, or 8th, 9th, and 10th, I'm still taking 15 possible runners, and I'm choosing 3 of them to arrange. No matter what place it is, whether it's first, second, third, 8th, 9th, and 10th, I'm still taking 15 runners, choosing 3, so the answer would be the same. All right. Now this last question here, a little preview of our next type of counting, but what if the runners were not competing for first, second, and third, but rather for 3 qualifying spots in another race? Say this was a semifinal race where there were 2 heats, and there were 15 runners in one heat and 15 runners in another heat, and the top 3 runners in each heat were going to advance. So we weren't taking 3 runners out of the 15 and assigning them first, second, third. We were just saying, well, how many different combinations of 3 runners can there be from 15? Is this going to be calculated differently? And if you think about that, the answer should be yes. It is going to be calculated differently because we're not arranging the runners in a first, second, third order. We're just choosing 3. That's what we'll look at here next. So we have these things called combinations. So combinations, if we take the number of combinations of n items of a set chosen r items at a time, is calculated this way. Capital C with a little n and a little r, subscript n, subscript r, means the same thing. We have n items, n total items, and we're choosing r of them to arrange. This is our formula. It looks almost identical except this one extra part. We have n factorial in the numerator. We still have the quantity n minus r factorial in the denominator, but we're going to multiply that quantity by an r factorial. Same conditions on r and n. But you can see now, when I have a 5 choose 3 combination, this is what it's going to play out. I'm going to have 2 factorials in the denominator that I will multiply together to simplify my expression. So if I go back to the last example here, we had, the first time we had a 15 choose 3 permutation, and that was going to be 15 factorial over 12 factorial. Well, now in a combination, we're going to have a 15 factorial, we're going to have r factorial, which is 3 factorial, then times 12 factorial. Okay, now if you think about the value of those 2 expressions, which one of those is a larger number? Well, in my permutation and combination, the numerators are the same, 15 factorial, 15 factorial. In the permutation, my denominator is 12 factorial. In my combination, my denominator is 3 factorial times 12 factorial. So in the combination, the denominator is going to be larger, which means the overall value of the fraction is going to be smaller. So when we have 15 items and choosing 3, we get more permutations than we do combinations. And that's because of the ordering or the arranging that we do. It adds some extra possibilities in there. Okay? So here are 3 examples, the wording of combination problems. How many different teams of 11 players can be chosen from a soccer team of 16? Well, we have 16 items, a combination because there's no ordering or arranging, we're just choosing 16 players. So we have the 16 factorial over 11 factorial, and then the difference of these two is a 5, so we have 5 factorial. Okay? If you expand it out and simplify, or you use your calculator, you're going to get 4,368 combinations. Okay, let's look at this third one here. A salad bar offers 8 choices of toppings for a salad. In how many ways can you choose 4 of them? So this is an 8 choose 4 combination. So if we were going to expand this out, we would do 8 factorial over 4 factorial. 8 minus 4 is 4, so another 4 factorial. And we could simplify this or expand this out much the same way we did in my previous slide. But if we were going to go ahead and calculate that with a calculator, we would get 70, or if we expand it out and simplify, we're going to get 70. So there are 70 different salads you can make when you have 8 toppings and you're choosing 4 of them. So the bottom line here is, the only thing that we have to take away from our problem is, does order matter? And the answer is yes, order does matter. If we're ordering or arranging, it's permutation. If not, it's what's called a combination. Hope you guys have a great day.